People sign bad contracts, chase useless treatments, and support broken policies because they misread data summaries. They think a single average or percentage tells the whole story and ignore who was measured, how spread out the values were, and what comparisons are fair. What is happening mathematically is they compress a distribution into a point, treat a noisy sample statistic as if it were the population truth, and condition on the wrong variables. You skim a report about a hiring test, see a clean average score at the top, and feel confident, not noticing that departments were mixed in a way that reverses the conclusion you actually need. Statistics is the craft of turning variability into statements you can trust enough to act on. It draws a hard line between the world you want to know and the data you actually have, then builds a bridge only as far as the data will support. It is not spreadsheet arithmetic. It is a way of asking what information the numbers contain and what they do not. When done right, it protects you from being persuaded by patterns that show up once by accident and from summaries that hide the important part. Data come from processes. People differ, sensors drift, choices are constrained, and timing matters. Randomness in statistics is not chaos. It is a tool for modeling the parts of the process you cannot track in detail. When you say something is random, you are not giving up. You are acknowledging you do not know which of many plausible outcomes will happen, and you build models around that uncertainty. Everything hinges on the distinction between a population and a sample. A population is the full set you care about, like all customers you might see this year. A sample is the subset you actually observed, like the people who answered your survey. The true quantity about the population is called a parameter. The number you compute from the sample is called a statistic. Descriptive statistics summarize what you saw. Inferential statistics say what those summaries imply about the population, with uncertainty made explicit. An education blog blasts a headline that a study shows a new method raises average test scores by 5 points. That sounds definitive, like free improvement you can bank on. The problem is that an average without context is a half sentence, not a conclusion. Without knowing who was measured, how they were chosen, and how much the scores were spread out, you do not know if that 5 matters for your setting at all. Here is the cost of swallowing that headline whole. If the volunteers for the new method were already motivated, you just measured motivation, not the effect of the teaching. If the study ran during a quiet term, you just measured calendar noise, not learning. If the test had a ceiling, gains at the top were impossible by construction. In practice, rolling out a program based on a headline average means you risk spending money and time to chase an effect that was never about the method. The correction is not complicated. Always ask who was in the sample, how they were selected, and who was left out. Ask how the values were distributed, clustered, spread, skewed, or split into distinct groups. Ask how the outcome was defined and measured. If possible, look at a picture of the distribution and a comparison group defined by a rule you can defend. A common beginner mistake is to treat counts and percentages as if they were self-explanatory. A bigger count can just mean a bigger pool was measured. A larger percentage can come from a tiny denominator and still be irrelevant in absolute terms. Rates hide choices about the denominator. Per person, per hour, per visit, or per transaction. Each tell a different story, and you will draw the wrong lesson if you ignore that choice. You avoid that mistake by always stamping a denominator onto any rate you read or speak. You say out loud what the rate is per what, so you hear whether it matches the question. You compare on the same basis across groups before you conclude anything. You also ask whether the comparison is fair in time and context because a rate across a holiday month does not map cleanly to a normal week. Small samples are another trap because they produce tidy averages that wobble a lot. A survey with 12 people can feel precise when summarized because the average looks the same each time you compute it. But run that survey repeatedly and the number lands all over, not because the world changed, but because tiny samples cannot settle down. If you make decisions from that kind of wobble, you will swing policies back and forth without learning anything. What looks like a decisive change can often be explained by ordinary variation when the sample is small. That does not mean you should wait forever. It means you treat early signals as hypotheses to test, not as facts to implement. Replication is not a formality. It is the mechanism by which noise separates from structure. If you think of every number as coming with a cloud around it, you will hesitate at the right times and push forward when that cloud is actually shrunk. Another source of confusion is mixing marginal and conditional statements. A marginal statement ignores important categories and pools everyone together. A conditional statement asks within each category. It is common for a trend to point in one direction within each group and the opposite direction when you pool the groups because the mix of groups changed. That move is not trickery. It is arithmetic doing exactly what you asked it to do while you asked the wrong question. Correlation is often sold as cause, and it bites anyone who wants quick stories. Two lines moving together could mean cause, shared cause, feedback in both directions, or just a schedule that drives both. When advertising spend rises with revenue, you might think ads cause sales, but it could be that budget rises when sales rise, and both respond to seasonal demand. And if you act on correlation like cause, you will push the lever that looks easy and wonder why the machine barely responds. Charts can mislead even when the numbers are correct. Starting the vertical axis at 98 turns a tiny change into a cliff and makes your eyes feel urgency that is not there. Smoothing away outliers can hide real problems that happen rarely but matter a lot. Truncating the timeline can make a swing look like a trend. When you read charts, you should look at axes, scales, breaks, and the choices that were made to turn a table into a picture. There's also the problem of hunting for a pattern until you find one. If you slice the data many ways, keep the slice that looks best and throw away the rest, you will create certainty out of noise. This is not a moral failing. It is a predictable result of many tries. The practical fix is to decide what you will test before you look, or to hold out a chunk of data to confirm any pattern you find after the fact. Without that discipline, yesterday's discovery will evaporate the moment it meets new data. Underneath all of this is measurement. You never measure the abstract thing, you measure an indicator that stands in for it. A productivity score is not productivity, it is what your rubric counts. A satisfaction survey is not satisfaction. It is how people answer today with this wording. Every statistical conclusion inherits the choices baked into the measurement, so you keep track of definitions, timing, and the ways people can game the metric. So what is statistics? Stripped down to basics. It is a map from data to claims that never forgets how much uncertainty is in the room. It says what you saw, estimates what that implies about what you did not see, and quantifies how wrong you might be if you generalize. It distinguishes signal from noise by demanding fair comparisons, clear denominators, distributions rather than points, and questions posed at the right level of conditioning. The most common beginner mistake in all of this is to rush. You see a number that fits your hope or fear and you stop asking questions. That habit is expensive. It locks you into brittle decisions, turns false positives into policies, and makes you vulnerable to anyone who can frame a plot to trigger the response they want. Slowing down to do a tiny checklist of questions is not ceremony. It is the cheapest way to avoid large errors. The actionable correction looks like this. Before you trust any headline or chart, ask who was counted, how they were chosen, and what outcome was measured. Ask how spread out the values are and whether groups were pooled in a way that flips the story. Stamp a denominator on any rate and check whether the axis scaling matches the question. If a pattern was found by exploring, treat it as a lead to be confirmed, not as a result to be rolled out. This connects directly to how we talk about centers of a distribution. When people say average, they usually mean the mean, and they expect it to summarize the typical case. In skewed data, or data with heavy tails, the mean pulls toward the rare extremes and stops representing anyone in the middle. The median can resist that pull, and the mode can tell you where the data cluster. Picking the center that answers your question is not an aesthetic choice. It is the difference between a summary and a distortion. The single shift in thinking to take from this lesson is that statistics is not about getting a number. It is about understanding a distribution, the mechanism that produced it, and the limits on what you can conclude. Once you see every reported number as a sample estimate wrapped in uncertainty, with a denominator and a context, you stop asking whether a result is true and start asking what claim is justified. That is the mindset that rescues you from confident mistakes and makes your inferences match your questions. Next, we go to mean, median, and mode, which average is actually telling the truth, so you can tell when each center matches the question you actually want answered.